Today we're going to do a brief review of solutions, and this is all stuff that you learned in honors chemistry, but I just want to make sure everybody's on the same page for building upon this for the AP content. So first, just a review of some terminology. So a solution is a homogeneous mixture of two or more substances or components. And you can see that here as in the third beaker, which has a dispersion of both blue and orange particles mixed together evenly. So remember, a homogeneous solution or homogeneous mixture is one where it doesn't matter which part of the beaker you pull the sample from, you get the same thing. So the top is the same mixture components as the bottom is. All right, and then a solvent is the majority of the mixture, and then the thing that you're dissolving in that solvent is called the solute. So in the picture I have here, the blue is the solvent. Usually in our cases in this class, usually the solvent is water, and then the solute is some other solid that we're dissolving in water. But there can be solutions that are not just a solid dissolved in a liquid. So for example, soda is an example of a gas dissolved in a liquid. That is also an example of solution. And you can have two gases mixed together. That's an example of a solution as well. So any homogeneous mixture, it doesn't matter what the phases of the components are. So as I said, what we're going to deal primarily with in this class are aqueous solutions. So that is a solution in which the water is the solvent, and you can have it a solid, a liquid, or a gas as the solute. So there are lots of examples of that in your everyday life. Everything from club soda to a simple syrup solution, that's just sugar and water, to if you were to dissolve some acetic acid in water and make vinegar, that's also an aqueous solution. So those are examples of solid, gas, and liquid dissolved in water. So solubility is the amount of the substance that will dissolve in a given amount of solvent. Okay, so far I just have had you learn the solubility rules that sodium, potassium, nitrates, and ammonia all dissolve. Okay, but there's a continuum there, so some amount will dissolve, and at some point, if you add enough sodium chloride, even though it's got sodium, it's not all going to dissolve. So the solubility is a measure of how much of it will dissolve in a given amount of solvent. And again, we covered this in honors chemistry as well. So one thing we didn't talk about too much in honors chemistry is how entropy relates to the formation of solutions. So entropy is the spreading out of energy, right? And so if we are taking a solid and dissolving it into a liquid, we are increasing the entropy of the solution, or the system. However, if we're taking a gas and dissolving it in a liquid, that's going to decrease the entropy. So it really depends on what your solute and your solvent are in terms of how the entropy is going to be a factor. Okay, and then here I have a table that shows you the relationship between the solvent-solute interactions and then the solvent-solvent or solute-solute interactions. So in order for a solution to form, the solute, which is connected to itself via intermolecular forces of some sort, needs to break apart. And it has to break apart some of the solvent-solvent interactions if it's going to interact with the solvent. So once the solution is formed, then we have interactions between the solvent and the solute. So the relationship between those two things tells us whether a solution can form or not. So if the solvent-solute interactions are stronger than the solvent-solvent and solute-solute, then we'll form a solution, because we've formed more favorable interactions when the solution is formed. If the two types of interactions are equal, generally a solution will form because that usually favors mixing, which is our entropy factor. So if the two types of intermolecular forces are pretty much equal, then we usually get a solution to form. And if the solvent-solute interactions are weaker than what you have in the solvent or in the solute alone, then sometimes you can get a solution because we have that entropy component, but not always. So it really depends on the conditions in that case. Okay, and then the last thing I want to touch on for this part is just like dissolves like, which we talked about in honors. And that just says that things that have similar types of interactions are going to be more likely to form solutions. So polar things tend to dissolve in polar solutes, and nonpolar things tend to dissolve in nonpolar solvents. Okay, so if the two things are polar, they're more likely to form a solution. And similarly, if it's an ionic compound, that's only going to dissolve in a solvent that's polar because it needs those partial charges to interact in order to create favorable solvent-solute interactions. So now to put this in a more quantitative perspective, the enthalpy of solution is the sum of all the changes in enthalpy for each step of our solution formation. Okay, so the delta H of solution, which is our enthalpy of solution, is going to be equal to the delta H for breaking up the solute, which is always going to be positive because we need to break apart those intermolecular forces in order to separate the solute molecules, plus the delta H for breaking apart the solvent, which again is going to be positive because we're going to break apart bonds in order to make room for solute, plus the delta H of mixing, which is always going to be negative. So when the solution forms, we're always going to have some new interactions that form, and it just depends on whether those interactions are greater than or less than the interactions we had to break in order to make the solution. So to sum this up and also link it back to the table we just did on the previous slide, if the sum of the endothermic terms is approximately equal in magnitude to the exothermic term, then the delta H of solution is going to be about 0. And so since we generally have an increase in entropy upon mixing, this will overall drive the system toward formation of solution. Okay, so if the sum of the endothermic terms is smaller in magnitude than the exothermic term, then delta H of solution is going to be negative, and the process will be exothermic plus driven by a increase in entropy, and so this will drive the formation of a solution. And then the third circumstance would be if the sum of the endothermic terms is greater in magnitude than the exothermic term, then the delta H of solution is positive, which means that the process is endothermic. And in this case, as long as delta H of solution isn't too big, we'll have a tendency toward forming a solution because it's an increase in entropy, but not always. So if the delta H of solution is too large, then the solution would not form. So one example of this is sodium chloride. So if you dissolve salt in table salt in water, you'll find that it gets cold. It's an endothermic process, but the delta H of mixing is exothermic enough that it will still happen because it's not a huge change in enthalpy. All right, so now let's just go over the terms that tell us what state we're in terms of how much solute is dissolved. So in a saturated solution, the dissolved solute is in dynamic equilibrium with this solid or undissolved solute, and we call that a saturated solution. So if you add additional solute to a saturated solution, it's not going to dissolve. All right, in an unsaturated solution, we have less than the equilibrium amount of solute, and so if you add additional solute, it will dissolve. Okay, and then under very specific circumstances, you can sometimes get a supersaturated solution. This is one that has more than the equilibrium amount of solute dissolved, but these solutions are very unstable. And usually, if you add any excess solute, it precipitates out the excess that was dissolved in the supersaturated solution. All right, so since we've just talked about how entropy is a factor in this, hopefully you know that if we're talking about the temperature of a solution that a solid is dissolved in a liquid, then the temperature is going to positively affect the solubility. That is, if you increase the temperature, more is going to dissolve. Okay, so we did a lab with this in honors chemistry, and probably from your everyday life you recognize this to be true. And for gases, however, because of the opposite relationship with entropy, you actually get the opposite effect with temperature. So when we increase the temperature of a solution where a gas is dissolved, the gas is going to be less soluble than if we decrease the temperature. So they're inversely related in that case. And then the last thing that would affect the solubility of a gas is the pressure. So as we increase the pressure, then we increase the solubility. Okay, because as we increase the pressure, we move those gas molecules closer together, and we are increasing the vapor pressure in the solution, and so therefore we are forcing more of those gas molecules into the solution. Okay, and you probably have experienced this before. If you open a soda, you release the pressure that it's under, and therefore the carbon dioxide begins leaving the solution, so it will eventually go flat. All right, and then last but not least, just reviewing concentration, which we've been using off and on all year, so this should not be really new for you. Okay, so a dilute solution is one that contains a relatively small amount of solute compared to the amount of solvent. A concentrated solution is one that contains a large quantity of solute relative to the amount of solvent. And then the molarity is the unit of concentration we use most often in chemistry. And the molarity is just the amount of solute in moles divided by the volume of solution in liters. Okay, so if we wanted to prepare a 1 molar solution of sodium chloride, that 1.00 capital M molar means that we have 1 mole per liter. Okay, so if we wanted to prepare 1 liter of this solution, we would need to add 1 mole of sodium chloride, which is 58.44 grams. You'd get that from your periodic table. And so to make that solution, and this is important because the AP test will sometimes ask you how you would make a solution. What you would want to do is you'd want to add the sodium chloride to your volumetric flask, and then add water until you get to a total volume of 1 liter. Okay, so you wouldn't want to add 1 liter of water to that 1 mole of sodium chloride, because in the end you'd end up with more than 1 liter of solution, and that's not what you want. You want exactly 1 liter. So you want to dissolve it as you go and then fill it exactly to the 1 liter line when you're done. All right, and then the last question is, what is the concentration of a solution that is prepared by dissolving 17.2 grams of ethylene glycol in water and brought to a total volume of 515 milliliters? So first we need to know the molar mass of ethylene glycol, and you can calculate that using your periodic table, and you'll get 62.068 grams per mole. All right, and then if we have 17.2 grams of that, we need to figure out how many moles that is, because we find concentration by doing the number of moles divided by the total volume. Okay, so 17.2 times 1 mole over 62.068 grams is 0.277 moles of ethylene glycol. All right, and then to get the molarity, we would divide by the total volume. So that's 0.515 liters, because we need to be in liters, not in milliliters. And if we divide that out, we get 0.538 molar, and that would be the concentration of our solution.